Hello and welcome. Today we're going to be looking at the integral from 0 to 1 of x to the power dx. And apparently this integral converges to this infinite series. I should have really put plus dot 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 there, but I didn't do it. I have actually done practically 80% of this work, in a previous lecture that involved the gamma function, because this question is all about the gamma function. So let's start with this particular integral and just see how we're going to attack it. And the way we're going to do this is we're going to write x dx, of course, as an exponential. Pardon me, my cough terrible today. Okay, so this we can write perhaps as e to the x log x. And then, of course, we have a power series for e to the something, and that e to the something, and now in enrichment, is the sum from r is equal to 0 to infinity, and the exponential function is, of course, the x to the n divided by n factorial. In this particular, that's, of course, sum r is equal to 0 to infinity. So in this particular case, is going to be x log x to the power, we're in r, so that's good enough so far. And then we have to assume that integration, summation, commute. So in this particular case, the do, and we can pull out the sigma. The integral is dx, so the 1 over r factorial can come outside the integral, but not, of course, outside the summation. And then we'll have the integral 0 to 1 x log x to the power of r dx. And I think this is really the only extra bit that we have in this question. I've done the integral from 0 to 1 of x log x to the power of r or n or whatever I used on that particular lecture when I've done gamma functions. So for this particular question, we now need to use a substitution. And the substitution we're going to use is t is minus the log of x. What I'm trying to do is I'm trying to sort out the limits to turn this into a gamma. So minus t is the log of x, and then we have x is equal e to the minus t. Probably it's easier to differentiate it from there. Dx is minus e to the minus t, and you will see what I meant about the limits. When x is equal to 0 and when x is equal to 1. If you look at what happens when x is equal to 1, when x is equal to 0, the log of x, when you're putting 0 in the limiting case, is minus infinity. With the minus, we'll switch into a plus. So, and when x is equal to 1, log of 1 is 0, the minus makes no difference. It will go to 0. So let's see what will happen now to all of this. We've got that bit on the outside. The limits have gone infinity and 0. And now the x. The x, I'm going to use exponentials. E to the minus t, that's the x there. The log of x is a minus t. By looking at this particular expression, put the minus on the other side. All of this will be to the power of r, and my dx is another minus e to the minus t dt. So a little bit of housekeeping now, try to tidy this up. First of all, I'm going to swap the limits. So do I have enough room? Probably have enough room to actually write it here. So the sigma, not really doing anything with it, so that's up to there. Now, so I'll do it in 2 steps. The minus we'll reverse, I'll do it in 2 steps. I will reverse the limits of integration. That's this minus here. And then I'm going to have e to the minus rt, that's this bit here. And then the minus has gone. E to the minus t, that's this exponential. And this is going to be a minus t to the power of r dt. And just rewriting this, we have 1 over r factorial. Now, this is annoying, this minus there. So if we pull it minus 1 to the r, okay, it has no t dependence. It can come outside the integral, but not, of course, outside the sigma. So I can write it as minus 1 to the r. This is from this bit here. And then the integral, not to infinity. And then we got e to the minus t r plus 1. That's the exponent of the e. And this has lost its minus. I pulled it outside, so it's t to the r. And of course, this is dt. And you can see there's another substitution coming now. I don't actually need this substitution, but in the time it takes me to make a bit of space, you can see that this is almost a gamma function. It just needs a gamma function, for example, as not to infinity, and it's e to the minus u to the x minus 1 du. So that's the gamma of x. So at the moment, the problem that we have is e to the minus, we need to have had just a minus t there. We have this r plus 1, it's not a problem. So we're going to call all of this mess a single letter. And since I have it in u up there, okay, let's call it u. So we got u is t r plus 1. Du is equal to, this is now a constant, so it's going to be r plus 1 dt, and my dt is what I'm trying to change here. So dt will be du over r plus 1. The limits will be unaffected, so limits unchanged. We can check it very quickly. Unchanged. And that's because, of course, if t is 0, looking at this integral, the u will become 0. And if t becomes infinite, positively infinite, then the r plus 1 is a positive number. And of course, the u will be infinite. So the limits will not change. Let's see what happens into all of this now. R is equal to 0 to infinity, 1 over r factorial minus 1 to the power of r. And this integral now will be 0 to infinity. We call this now e to the minus u, but the t changes, so I have a little bit more work to do. I thought I was done, but unfortunately I'm not. T from this line here is u over r plus 1, so that's this t here. And annoyingly, is powered up on top of that, so it's just a bit of a pain, really. R plus 1 there. And what do we have for this particular one? Do we have to the power of r so far? Yeah. And sorry, what else we got? And the dt very quickly. The dt is du over r plus 1. I think I'll go all the bits and pieces in there. So I hope this bit is visible still on the video, so because I know the page is actually cropped up and it doesn't actually show my entire tablet in there. So first of all, minus 1 to the power of r divided by r factorial. And now this integral, if we look at what we're going to get, r plus 1 and r plus 1, they have no u dependence. So I can pull them again outside this, and I'm going to have 1 over r plus 1 to the power of r plus 1. I hope we can all see where that is coming from. That's the r plus 1, the 1 over rather, to the power of r, but I've got another 1 over that, so that will make the extra plus 1 in there. And the integral now is purely a gamma function, e to the minus u to the r du. And this is now by definition a gamma function. Which gamma function that is? He always cuts me sometimes. I make mistakes on this bit here. Minus 1 to the r divided by r factorial, r plus 1 to the power of r plus 1. And we have the gamma, and this is the gamma of r plus 1. One more, because in the definition we have a minus 1. And of course, in this particular case, I think I'm going to rub off these bits in here. We don't need them. Maybe we can just about squeeze it and don't have to rub off anything else in this particular question. If r is, of course, is a positive integer, so this is actually an integer in there. This is simply r factorial. So probably I will just not write it again. I will say this is simply r factorial. Oh, I wrote it really badly and it looks like it's on the denominator there, so let me just not write it like this. It's quite stupid really. I've done this before and I cancelled it, or I've done the wrong thing because of these little explanations. So this is my r factorial, and therefore I can cancel this. R factorial there and R factorial in the denominator. So this gives me to be equal sigma from r is equal to 0 to infinity. We have alternating terms, and at the bottom we have r plus 1 to the power of r plus 1. And I hope if we check this, we are getting this particular expression. You can write this differently if you prefer it. It doesn't really matter whether you got it from 0 or from 1 or whatever. It's the same, by the way, if you shift the origin essentially. R is equal to 1 to infinity. Probably I would have written it a little bit different. I would have started summation from R is equal to 1, and I would have written it as R to the R, and I would have therefore written this as R plus 1 or R minus 1. It hardly matters. So something like this is also the same summation. Okay, and I think both of these should be giving you the series that we got there. I hope you enjoyed this particular video. It did require gamma functions. I didn't mention it, but it's quite advanced stuff and quite interesting, trying to motivate you and get you to see some of the stuff and some of the applications of beta and gamma functions that I've done a few lectures recently. Okay, I'm going to be signing out. I'll see you real soon. Bye for now.